Okay, so hey guys, I just want to create this quick tutorial to teach you guys how to create a thrust vectoring mount, because when I first started out uh, creating this thrust vectoring system, there weren't very many tutorials specifically focusing on thrust vectoring and sort of PID control using servos. There are a lot of PID tutorials using like thermistors and electric motors. It's not too difficult to transfer that PID theory and knowledge and code into a servo controlled thrust vectoring mount. Alright, so let's start off with the hardware. So as you can see, this is only a single axis thrust vectoring system. Unfortunately, due to COVID, I wasn't able to get access to the secondary servo motor required to make a proper dual axis thrust vectoring system. However, I'll show you later on in the video that it's actually not that difficult to, at least in terms of the code. It's literally just copy paste the code for this axis into the second axis. That's really not quite difficult. And then I'll show you a good mount design to get that dual axis started. But anyways, so I'm assuming that you guys already know PID control. This tutorial is just a tutorial on implementing the implementation of PID, and I'll link some great tutorials in the description down below if you guys still don't really understand theory. But this is just to show you how to implement PID control in a thrust vectoring system. So the two main components of a thrust vectoring system are the servos. In this case, only one servo, but usually there are two servos. And then there's the IMU, or inertial mass unit. The one I have here is called the MPU 6050. However, there are definitely better IMUs out there on Amazon. I'll link the places where I got them from also in the description. But anyways, linking the servo is quite simple. So as you can see, we have three cables. Sorry. Yep, that's better. Okay, so the three cables connecting the servo to the Arduino board. So there's a power, the ground wire. Those are quite obvious. You just connect it to the power and the ground respectively. And then you have the sort of the control wire, you have to connect this wire to a PWM pin or slot. As you can see here, I've connected mine to the 9th PWM slot. And then that will pretty much gear you up for the thrust vectoring system. If you had a second servo, you'd replicate this entire setup, just connect it to a different PWM pin, obviously. Also, just a quick note, this component here, it's called a capacitor, and you definitely do want to get this and put it on your servo, mainly because servos, while they operate, they take up much more current than the board is really capable of. So what a capacitor does, if you don't know, it stores that sort of extra charge and prevents it from overloading the board. So you definitely want to get a capacitor here, or else your board might burn up. And also don't forget to connect the capacitor in the right direction. So if you don't know, this the white or the black stripe on the capacitor represents the ground side. So just match the stripe to the ground wire and you'll be set. Okay, so the next part then it would be the IMU itself. Now I have a MPU 6050, like I said, but this same sort of pins should pins should be same in any board, any IMU, but all you want to do, it's quite simple. You just if you look at the board quite carefully, it'll show you some. It'll be a bit hard to see on camera, but if you look at the board, there are some names. So for example, the first one says VCC ground, SCL, SDA. And all you want to do is connect the respective pins here into the Arduino. So for example, the Arduino here, it has the SCL and SDA pinholes. You just want to connect those straight into the board. Now note here, I don't have access to soldering, so all I'm doing is using some of the I believe they're female to female wires in order to connect the MPU to the Arduino. But I will highly recommend you guys get solder if you're getting an unsoldered breakout board like I did. This is because it's difficult to get a good connection with the MPU board because it's quite sensitive. And without solder, it's literally like every test that I've done, it always disconnects. So you definitely do not want to pass up on that solder. I think that about does it in terms of hardware. Of course, you in a proper thrust vectoring mount, you'd attach whatever you want. Well, you'd attach the nozzle, presumably, to the thrust vector mount, which I've tried to simulate here with a bit of soda cans. And yeah, now I'll talk about the software side. So before I do get on to the actual PID code, I'd just like to show you guys a code that I found super useful. So this is called the I2C tester, and basically all it does is uh, show you if you have a secure connection to the MPU 6050. So for example, I'll show you right now. If you open the serial monitor, it'll uh, keep essentially scanning for ports, for I2C ports, and once it finds a connection, it'll show up as successful, and I'll just give you a demonstration of that. So as you can see here, it's found an I2C device, so that means you have a secure connection. Of course, if you soldered your connections on the MPU board, you don't really need this. However, if you're like me and you don't have a solder, then this code was just a lifesaver for me. So hopefully you find it useful. So getting on to the actual PID control software then, I'll just go through sort of line by line to the code. So you have this sort of servo importing all the libraries for to use to control the servo on the top here. Uh, then you have all the variable initializations. So here we're creating an integers with 16 bits for the acceleration and gyrometer. The reason we need arrays is because the data from the MPU, it doesn't come as one value, comes as two, as I'll show you further on, and you need to sort of add them together. And we just got some time initialization, time variables, and then the actual PID values, which will start off with 0. Here are the PID constants, and basically what they are just multipliers of um, each feedback sort of feedback signal. So again, I'm assuming you guys know what I'm talking about here. So the PID uh, feedback comes in three signals: the proportional, integral, and derivative, and these constants determine how much each signal is weighted. And here we have the desired angle. 0 on the MPU board means that you're horizontal um, with the ground, and I have 90 here and with my server because uh, at 90 you essentially get the full rotation of the servo that I'm using, but you'll have to test out and see which angle works best for your server because you might have more sophisticated servers than I do. Now we're starting a communication with the MPU board. Here we have the address of the MPU board, and then just doing some basic servo actions. So initializing the servo on pin PWM pin 9, and then setting it to start off at our desired angle. Well, here this time equals millis in brackets is just the time elapse, and we will need that of course for our derivatives and integrals, and we'll just put a delay at the end so that we have some time for everything to start up. And so here this code will just give you the actual time that's elapsed. We divide by 1,000 at the end to convert from the signal into seconds. This is the actual um, accessing the registers in the MPU in order to get our values for the angles. And this is what I was talking about earlier. You know, each value sort of there are two values in each sort of input because there's two registers and you have to combine these two in order to get a proper value. And then you get your angle theta by using what's called the um, Euler formula in order to convert from raw data and into angles that we can actually use. And then we can print out our angle just to, for testing. And so all that code is just like taking in the values and setting up constants and all that. Here is the actual PID code. All you need to do to calculate the error is subtract our measured angle by the desired angle that we want. And then we use this value, the error value, to calculate like each of our um, sort of our signals. So for example, here for the proportional signal, feedback signal, we just take our constant and multiply it by the error, because a proportional, that means that you just want to take whatever error there is and multiply it by proportionality constant and then use that for control. Then we have the integral bit, which is basically just you if you have an error, a steady state error, then this will be really useful. Now I just put an if minus if statement here to sort of limit that integral to within an interval of 200 degrees, because uh, basically it doesn't really apply for us in this project, but if you don't use this if statement, then you're in danger of causing a what's called integral wind up, sorry, which is basically where if you if your error sort of is above what your actuator can perform, you get a buildup of this integral feedback, which will take time to fix in your system. And so this quick fix, I think it's called clamping, where you just eliminate that wind up from occurring in the first place by limiting your system with your inputs to within what your actuator can actually handle. Um, then lastly, you have your derivative control, which you just take the error and divide it over time. It's because the rate of change of the error. And then for the final PID value, you just sum all of these feedbacks. Um, and then you put that um, you want to take that value and use that to control your servo. So all you do is you subtract your inputted error by your you subtract your desired error by your PID value, and that will cause it to uh, will make your servo correct, essentially. Uh, and then at the end, we just store the previous error. So as you can see, this code is quite simple, much simpler than you might think it. Hopefully you guys find this useful. I definitely wish that someone had posted a tutorial like this, because there aren't many, at least that I've found, which show you exactly how to create a thrust vectoring um, system. So I'll link all the code down below, of course, and again, if you need a refresher on PID control, I'll link some tutorials to that as well. Then I'll quickly show you how to replicate this code for 2 axes, and I'll also show you quickly a good thrust vectoring system mount. Okay, so I've just edited the software very slightly. As you can see, I've created 2 objects, one for the X server and one for the Y. I've added a few more variables to store all the separate X and Y PID values. Uh, so it's literally just a copy paste if you want to get a dual axis PID control as you require in a thrust vectoring system. I just changed the names a bit, and the code is literally just the same. I've just copy pasted it, just added X and Y for, to account for each axis. Once again, I will uh, upload all of this code exactly as you see now. I'll upload it. It'll be in the description.